Null and undefined bugs can make TypeScript feel safer than it really is. In this video, we will go through 14 real mistakes junior developers make, see the broken code, understand why it fails, and fix it step by step. We start with the most common null safety mistakes, using a value before checking whether it actually exists. Imagine we receive a user from an API and the name field is optional. Here the code forces TypeScript to trust us, then immediately calls a string method. Now we run it and the script fails because the value was never there. Let's break down the result. Optional fields really can be undefined, and undefined does not have string methods. The compiler warning was useful here, and ignoring it moved the bug into runtime. Now we fix the code by using optional chaining and a fallback display name. If name exists, we uppercase it. If it is missing, we print anonymous, and now the run is stable. The better pattern is to make absence explicit at the point where you use the value. Use optional chaining when the next operation depends on the value existing, and pair it with a fallback when the UI needs something printable. As a quick practice, add a real name to the user object and run the fixed version again. You should see the uppercase name, which proves the fallback only runs when the value is missing. Here the backend sends null when the user has no avatar. The code only checks for undefined, so it misses the actual missing value. Now we run it and get a misleading message. Let's look at the condition. Null and undefined are different values, so a strict undefined check does not match null. The bug is not syntax. It is a mismatch between the data contract and the condition. Now we fix the condition to treat null and undefined as missing. In this specific case, the loose null check is intentional and useful. We run it again, and the fallback branch is selected. The best practice is to define what missing means in this part of the app. If both null and undefined mean no value, encode that rule clearly with value null, or with an explicit two-part condition. For practice, widen the type so avatar URL can also be undefined. Then test null, undefined, and a real URL to make sure your condition matches the rule you want. Next, we look at function inputs, where null can slip in from forms, APIs, or older JavaScript code. This example looks harmless. We want a guest greeting when no name is passed, but a form field or API payload might pass null instead of leaving the value undefined. Now we run the function and the output shows the default was not used. Let's explain the behavior. Passing null is still passing a value, so JavaScript does not use the default parameter. That is why the string interpolation prints null directly. Now we fix the function by accepting the real input shape and normalizing it inside. The nullish coalescing operator handles both null and undefined. When we run it, the greeting uses guest. The better approach is to normalize inputs at the boundary of the function. Use a default parameter when only undefined is expected, and use nullish coalescing when null is also a valid missing value. Try 3 calls. One with undefined, one with null, and one with a real name. The first 2 should print guest, and the real name should stay unchanged. Now we move to fallback values where the wrong operator can silently replace valid user settings. Here 0 is a valid setting because the user may want no retries. The code uses logical OR to apply a default, but OR does not only check for missing values. Now we run it and the configured 0 is replaced. Let's break down the mistake. Logical OR falls back for false, 0 empty string, null undefined, and NaN. That is too broad when 0 is meaningful. Now we switch the fallback to nullish coalescing. This keeps 0 because 0 is not null or undefined. When we run the fixed code, the configured value survives. The best practice is to use the operator that matches your rule. If only missing values should use the default, use nullish coalescing. Save logical OR for true Boolean style conditions. For practice, change retries to 2, undefined and null. You should see that the fixed version preserves real numbers and only uses the default for missing values. Finally, we look at optional fields from external data, where TypeScript types can be convenient but still require runtime care. Here we process an order summary from an API, and the discount code may be missing. The broken code forces the optional field to act like a string and reads its length. Now we run it and hit a runtime error. Let's unpack this. Optional properties are useful because they tell us the field can be absent. But once the data comes from outside the app, we need to code for that absence instead of trusting the happy path. Now we fix the calculation with optional chaining and a numeric fallback. If a discount code exists, we read its length. If it is missing, the length becomes 0 and the script completes cleanly. The best practice is to treat external data as untrusted at the point where you use it. Optional fields should be guarded, normalized, or given a clear fallback before calculations or rendering. For a quick variation, add a real discount code to the order. The same fixed line should now print the actual length, which means it handles both branches safely. Now we are entering TypeScript escape hatches. These are tools that can be useful, but they can also hide real runtime bugs if we use them too casually. This comes up when a developer knows a user should exist and reaches for the exclamation mark. We write a lookup with find, force it with the non-null assertion, and then read email right away. Now we run the script with a missing ID and the compiler stays quiet, but the runtime does not. Let's break down why this failed. Array find returns undefined when there is no matching user, and the exclamation mark only removes TypeScript's warning. It does not protect the code, so the email access happens on undefined. Now we fix the bug by keeping the result in a variable and checking it before touching email. This makes the missing user path visible in the code. Now we run it again and the program reports the domain problem clearly. The better approach is to use the non-null assertion only when the invariant is truly guaranteed and documented. For user input, database results, and searches, write the guard. That gives you safer code and a clearer error path. Next, we look at collections and lookups. These bugs happen because a lookup API often returns undefined when the key or item is missing. This example is a checkout price lookup. We create a map of known SKU prices, then ask for an unknown SKU and immediately call to fixed. Now we run it, and the missing key turns into an undefined value. Let's unpack the problem. Map get returns number or undefined. Because the key may not exist, the price formatting is fine only after we know we really have a number. Now we fix it with a single checked value. We read the price once, check for undefined, and only format it after the guard. Now the script gives a clear checkout message instead of crashing. The best habit is to treat every lookup as something that can miss. Use the same thinking for map get, object indexes, cache reads, and database results. Once the missing path is explicit, the happy path becomes much safer. Here, the customer has a selected plan ID and we search for that plan in an array. The bug is that we immediately read price from the find result. Now we run the script with a missing plan ID and see the crash. Let's look at what find really returns. If the selected ID is not present, the result is undefined. The property access is the unsafe part, not the search itself. Now we keep the found plan in a variable and branch on it. If there is no plan, the user gets a clear message. If there is a plan, TypeScript knows it is safe to read price, so let's run it again. The best practice is simple. After find, narrow before accessing properties. This keeps stale IDs and missing records from becoming runtime crashes. It also makes the missing state obvious to the next developer reading the code. Now we move to object handling. Nullish objects are especially tricky because the crash can happen before a default property value ever gets a chance to run. This is a settings loader that may return null when there is no saved configuration. We try to give theme a default value during destructuring. Now we run it, and the default never helps because the object itself is null. Let's break down the order of operations. JavaScript must first destructure from an object. The property default only applies after that, so null causes the crash before theme can fall back to light. Now we fix the destructuring by defaulting the whole object first. If settings is null, the code destructures from an empty object, and then the theme default can do its job. Let's run it and check the output. The best practice is to default the source object when the source may be nullish. Use property defaults for missing properties, and use nullish coalescing for the missing object. That keeps both levels safe. Finally, in this batch, we look at nested data. Deep object paths are common with API responses, and each nullable level needs to be handled deliberately. This example reads the shipping city from a user object. The user exists, but the optional profile does not. We access profile, address, and city as if the whole path is present, then run the script and hit the missing level. Let's trace the path. User is defined, but user profile is undefined. The next access tries to read address from undefined, so the code fails before city is even evaluated. Now we fix the path with optional chaining at each nullable level. If profile or address is missing, the expression becomes undefined, and the fallback gives us a clear display value. Now we run it and get a safe result. The best practice is to use optional chaining at every level that can be missing, then choose a fallback that makes sense for the product, like unknown city for display. Do not hide important missing states when the app should instead ask for shipping details. In this section, we look at how TypeScript narrowing can still fail when the runtime check is too weak. In real APIs, a query parameter like limit can be 0, and 0 may be a valid value. Here we write a quick guard with if value, then we run the script and look at what happens. The null case is rejected, but 0 is also treated as missing. Let's break down why this result is wrong. JavaScript treats 0 as falsy, so TypeScript narrows the branch. But the business rule is different. We only wanted to reject null and undefined, not every falsy value. Now we fix the guard by checking value not equal to null. This is intentional. It rejects both null and undefined, but keeps 0. Now we run it again and the terminal matches the actual rule. The best practice here is to use a guard that matches the exact values you want to reject. Use value not equal to null when only null and undefined are invalid. Save truthiness checks for cases where every falsy value is truly invalid. Now we move to async code, where nullable values are easy to miss because the value arrives after a wait. This is a common database pattern. A lookup returns a user, or null when no row matches. Here, we await the result and then access email as if the user always exists. Now we run it with an ID that is not found, and the program crashes. Let's explain the failure. Await only unwraps the promise. It does not guarantee that the resolved value is a user. The exclamation mark silences TypeScript, but it cannot create an email property on null. Now we fix it where the value becomes available, right after await. If the user is null, we print a clear message and return early. When we run the script again, there is no crash. The best practice is to treat awaited nullable results exactly like normal nullable values. Narrow first, then use the value. This keeps database misses and API misses as normal control flow instead of runtime crashes. In this section, we handle data that comes from outside TypeScript, where type annotations alone cannot protect runtime values. This example looks like cached user preferences from local storage or a JSON file. We parse the JSON and assert it as user preferences, then we use email like a string. Now we run it, and the null inside the JSON breaks the program. Let's break down the problem. JSON parse returns data from the outside world, and TypeScript types do not exist at runtime. The assertion changes what TypeScript believes, but the actual email value is still null. Now we fix it by parsing into unknown and checking the shape before using it. The validator only accepts an object with a string email and a supported theme. When we run this version, the bad cache value becomes a clear validation message. The best practice is to validate external data before treating it as your internal type. This matters for JSON, local storage, API responses, and files. TypeScript helps after the boundary, but you still need a runtime check at the boundary. Finally, we look at optional callbacks, where a small API design choice can decide whether a reusable function is safe. Here we are building a reusable file processor with an optional progress callback. The caller is allowed to pass no callback, but the function still calls it directly. Now we run it without the callback and the function crashes halfway through. Let's explain the crash. The question mark in the type means on progress may be undefined. The exclamation mark only removes the compiler warning. It does not provide a function at runtime. Now we fix it with optional call syntax. If the callback exists, it runs. If it is missing, the line simply does nothing. We run both cases, first without a callback and then with one. The best practice is to use optional call syntax for optional callbacks. It keeps the API flexible without making every caller pass an empty function. Also keep the callback type precise, so the callback receives exactly the data it needs. Now you know how to spot and fix the most common null and undefined bugs in TypeScript. Like the video, subscribe to Dev Level Up, and write in the comments which TypeScript topic or bug pattern you want to see next.